If you like our content, please like, subscribe, and click the notification bell to get alerts when we introduce new videos.
In this training, we'll go into detail on how OFDMA creates a more efficient payload delivery system. It allows multiple users with varying bandwidth needs to be served simultaneously. 802.11a to 802.11ac and the standards in between use OFDM to deliver Wi-Fi data packets. Using OFDM, devices use a fixed 20, 40, 80, or 160 bandwidth spectrum to deliver packets regardless of what's being transmitted over the wireless network. We'll use the simple analogy of using trucks to illustrate the difference between OFDM and OFDMA. Each of these activities are represented as a same-size truck forwarding data, even though the payload might not be the same size and the trucks might not be full. All three have to contend with road availability, which causes OFDM to be inefficient of the use of its bandwidth, because there could be empty space that could be utilized within each truck. 802.11ax, in contrast, uses orthogonal frequency division multiple access, which divides the frequency into resource units, maximizing the number of subcarriers or tones based on the spectrum available, which then divides the bandwidth based on the needs of each client, allowing simultaneous transmission of each client's data. OFDMA cuts the need for 3 trucks, but rather a single truck, potentially filling it to capacity based on its allocated resource units. This creates a payload delivery model maximizing the bandwidth use. Let's go into more detail on exactly how this is done using 11ax. We'll start by defining some of the terms and concepts. Multi-user applies to multiple technologies in the 802.11ax. So it's important to understand that the term multi-user does not reference a specific technology such as multi-user MIMO. It means that the transmissions between an AP and a multiple Wi-Fi clients can occur simultaneously, depending on the supported technology. 802.11ax defines the use of multi-user orthogonal frequency division multiple access, or multi-user OFDMA, and multi-user multi-input multi-output, or multi-user MIMO technologies. OFDMA is a multi-user version of OFDM in that it allows multiple users to share the available bandwidth and transmit simultaneously. With older OFDM, multiple users were separated in time domain only. Each AP can speak with only one device at a time, giving a single user the entire bandwidth, regardless of the packet or channel size. As such, they are client-centric with randomized, contention-based approach that regulates Wi-Fi to free-to-send, first-come basis. As a result, there might be wasted spectrum if the payload size of the client packet is small. In contrast, OFDMA is AP-centric. It enables an 11ax AP to simultaneously communicate with multiple devices by dividing each Wi-Fi channel into smaller subchannels called resource units, also known as RU tones. The minimum size of one RU is 26 tones, which equals approximately 2 MHz in size. Therefore, considering some overhead, a 20 MHz channel can serve up to 9 users at the same time. With OFDM, the transmission of data happens within a single time slot from a single client. As mentioned, OFDMA allows multiple clients to transmit simultaneously on their allocated RUs, but still must be performed within a single time slot. This requires coordination to ensure that the clients not only transmit at the exact same time, but also the same amount of data. This coordination is provided to all devices using a trigger frame. This trigger frame not only synchronizes all transmission, but also identifies the RU assignments, allowing clients to identify which subchannels they should be listening or sending on. The access point determines how to allocate the subchannels, as individual RUs can be utilized for different clients that are serviced simultaneously. Therefore, an AP can choose to allocate the whole 20 MHz subchannels to a single user in each time frame, or it may partition the channel, allocating RUs to multiple devices, allowing them to simultaneously transmit. This technique improves the usable throughput of all devices connected to the AP. This reduces the use of the contention methodology that preceded the 802.11ax and moves Wi-Fi from a contention-based to a schedule-based service. This helps stabilize Wi-Fi performance, especially in higher density environments such as stadiums, convention centers, transportation hubs, and auditoriums. OFDMA is most useful when multiple connections transmit limited amounts of data, which allows a protocol to squeeze smaller data packets through multiple subchannels or resource units. Think of a delivery truck that can only send a package to one house at a time, versus that same truck able to carry multiple packages to multiple houses. Moreover, OFDMA is effective at all ranges, close, medium, and far, and can help mitigate overlapping basic service set interference issues. A 20 MHz OFDMA channel consists of a total of 256 subcarriers. These subcarriers, or tones, are grouped into a smaller subchannels known as resource units, with a minimum size of 26 subcarriers, which will accommodate up to 9 users for every 20 MHz bandwidth. For example, when subdividing a 20 MHz channel, an 802.11 AP designates 26, 52, 106, or all the 242 subcarrier resource units, which equates to roughly 2 MHz, 4 MHz, 8 MHz, and the 20 MHz channels, respectively. An 802.11ax AP dictates how many RUs are used within a 20 MHz channel, and different combinations can be used and different sizes can be assigned to each client based on their bandwidth needs. Here we show a 40 MHz channel. There are 512 available tones, or subcarriers, in a 40 MHz channel. One tone equals a single subcarrier of 78.125 kHz. For high bandwidth applications such as video, the AP can decide to allocate the entire channel to a single user. This would be the same as current Wi-Fi 11AC for a given time slot. Or the AP may serve 2 users simultaneously, each occupying 242 tone resource units, each being approximately 20 MHz in size. For small packets such as IM or voice over Wi-Fi, the AP will mix and match different RUs based on traffic types. It can also divide up the resources all the way down to 26 tone RUs and in theory serve 18 users simultaneously. As you can see, OFDMA enables efficient use of available spectrum, especially for low bandwidth applications. Here we see the number of resource units or data tones available for an 80 MHz channel. We have up to 996 usable tones. This bandwidth allocation is effective in dense user environments where traditionally users would contend for their own turn to use the whole channel. With OFDMA, it potentially serves these clients simultaneously. This table shows the number of users that can now get frequency multiplexed access when the 11AX AP and stations coordinate for multi-user OFDMA operation using the 20, 40, 80, and even 160 spectrum. The RU tones currently defined are 26, 52, 106, 242, 484, 996, and 2 by 996 tone RUs. Let's discuss the Downlink OFDMA frame process. The downlink process begins with the AP contending for airspace, and then will send a multi-user ready to send across the whole channel for legacy devices to understand. This trigger provides the RU assignments to the STA it intends to send to, while providing a sync for all STAs for the following data transmission. Once received by the identified STAs, each will send a clear to send back to the AP on their designated RUs. The AP will then forward the data to each STA simultaneously on the STA's assigned RUs. Once complete, the AP will then send a block ACK request, again using the whole channel, and then each STA will send back its block ACK back to the AP along their assigned RUs. In OFDMA, the uplink transmission is very different in that it is scheduled-based transmission, and the AP is in full control of the scheduling. This is done to maximize uplink transmission efficiency. First, the AP transmits the control frame, called a trigger frame, to all users, which contains scheduling information, including the resource unit allocation to be used by each station. There are 7 different trigger frame types, like buffer status report polls, multi-user request to send. However, the main purpose of the AP basic trigger frame is to allocate resource units to clients. The RU allocation information is communicated to clients in both the PHY and MAC layers, mapping clients to their respective RUs. The trigger frame also indicates the number of spatial streams and power control information, such as individual users can increase or reduce their transmitted power. In response to the trigger frame, the multiple stations transmit simultaneously to the AP using the high-efficiency trigger frame format. To prevent interference, the packet's transmission from each of the stations must start and end at the same time, and they must remain synchronized in all times. Once the AP receives the frame from all stations, the AP sends back an ACK frame to finish the operation. You could say that the trigger frame is the master scheduler. Let's look at this in detail. The uplink process begins with the AP attending for airspace and then sending a buffer status report poll. This allows the AP to evaluate what RU allocation needs to be done to accommodate each station needs. Once the stations respond with their BSR, the AP will then send a multi-user ready to send and await for each STA to respond from its assigned RUs with the BSR. The AP evaluates the bandwidth needs of each station, and if it identifies a larger buffer queue on any of the stations, the AP may assign a larger RU for its use. The multi-user ready to send is sent to the stations to again assign RUs, which can be different from the previous trigger values. However, it is simply used to sync all the stations and receive the clear to sends from each. The third trigger again assigns the RUs to the stations, which can be different size to accommodate buffer queues that were reported from each, and to sync all the stations to begin their transmission. As mentioned, all stations need to send data in the exact same time and also with the same length time. This may cause some of the stations that do not have the same size PPDU to add padding to the end of the frame to ensure that it transmits the same length of time as others. This padding is identified and discarded at the AP once it's received. Lastly, the AP responds to all the stations with a block ACK using the full 20 MHz channel for legacy device support. So to summarize what we have described in the past several slides, I mentioned earlier that the world is going to look different with 11AX, primarily because of OFDMA. This is a figurative way to look at it. Today's world is represented by the picture on the left. There are a lot of multi-lane highways where everyone's trying to grab their space, and it's not the most efficient way. With OFDMA, the scheduled access, things look more like the right-hand side. It's all controlled. The AP decides who's next when dealing with the 11AX clients. Things look a lot cleaner. That's what's happening in the cellular networks today. OFDMA is very widely used today. We live in a world where there easily used spectrum in a cellular world that never gets allocated to the same device. They only get little chunks of the spectrum. With OFDMA, because of the scheduled access, things like QoS and other things are moved under the AP's control. It's not like a free-for-all. The AP will say which 11AX clients gets more spectrum. The AP becomes the master and the Wi-Fi communication becomes more and more complex, but also provides greater efficiency of the Wi-Fi spectrum.